For the first time, physicists have observed novel quantum effects in a topological insulator at room temperature. This breakthrough, published as the cover article of the October issue of Nature Materials, came when Princeton scientists explored a topological material based on the element bismuth. The scientists have used topological insulators to demonstrate quantum effects for more than a decade. But this experiment is the first time these effects have been observed at room temperature. Typically, inducing and observing quantum states in topological insulators requires temperatures around absolute zero, which is equal to minus 459 degrees Fahrenheit or minus 273 degrees Celsius. This finding opens up a new range of possibilities for the development of efficient quantum technologies such as spin-based electronics, which may potentially replace many current electronic systems for higher energy efficiency. In recent years, the study of topological states of matter has attracted considerable attention among physicists and engineers and is presently the focus of much international interest and research. This area of study combines quantum physics with topology, a branch of theoretical mathematics that explores geometric properties that can be deformed but not intrinsically changed. The novel topological properties of matter have emerged as one of the most sought after treasures in modern physics, both from a fundamental physics point of view and for finding potential applications in next generation quantum engineering and nanotechnologies. The main device component used to investigate the mysteries of quantum topology is called a topological insulator. This is a unique device that acts as an insulator in its interior, which means that the electrons inside are not free to move around and therefore do not conduct electricity. However, the electrons on the device's edges are free to move around, meaning they are conductive. Moreover, because of the special properties of topology, the electrons flowing along the edges are not hampered by any defects or deformations. This device has the potential not only of improving technology, but also of generating a greater understanding of matter itself by probing quantum electronic properties. Until now, however, there has been a major stumbling block in the quest to use the materials and devices for applications in functional devices. There is a lot of interest in topological materials and people often talk about their great potential for practical applications, but until some macroscopic quantum topological effect can be manifested at room temperature, these applications will likely remain unrealized. This is because ambient or high temperatures create what physicists call thermal noise, which is defined as a rise in temperature such that the atoms begin to vibrate violently. This action can disturb delicate quantum systems, thereby collapsing the quantum state. In topological insulators, in particular, these higher temperatures create a situation in which the electrons on the surface of the insulator invade the interior or bulk of the insulator and cause the electrons there to also begin conducting, which dilutes or breaks the special quantum effect. The way around this is to subject such experiments to exceptionally cold temperatures, typically at or near absolute zero. At these incredibly low temperatures, atomic and subatomic particles cease vibrating and are consequently easier to manipulate. However, creating and maintaining an ultra-cold environment is impractical for many applications. It is costly, bulky, and consumes a considerable amount of energy. But the Princeton researchers have developed an innovative way to bypass this problem. Building on their experience with topological materials and working with many collaborators, they fabricated a new kind of topological insulator made from bismuth bromide, which is an inorganic crystalline compound sometimes used for water treatment and chemical analysis. This is just terrific that researchers found them without giant pressure or an ultra-high magnetic field, thus making the materials more accessible for developing next-generation quantum technology. The researchers believe their discovery will significantly advance the quantum frontier.